Welcome back. So this lecture and perhaps the next two lectures are going to be one of the most fundamental lectures that we will keep repeating in terms of usage of these results throughout the course in some form or other, right? So we have seen how ordinary differential equations can be used to model systems, and we saw the existence and uniqueness of such models and what it means, in terms of relevance to, say, a physical system. And eventually we try to understand the dynamic behavior. I mean, there are, the nonlinear behavior especially can be quite complicated, and eventually we reached a point where we said wanting stability of an equilibrium point is important thing for control systems. And then we defined the notion of Lyapunov stability, asymptotic stability, exponential stability, and their global versions, right? But if you look at the definitions, is it easy to verify those? And then we will look at a couple of examples first, and then understand how one can actually test for stability without really thinking about the basic definition, right? Take a very simple example, right? So something like x dot is equal to, let's say, minus x, right? And if you have something like this, then we know that the solution for this is e raised to minus t x 0, where x 0 is the initial condition, right? So what are we trying to show? Well, let's see. I mean, of course, clearly the only equilibrium point is the 0 solution. So that means if you start at 0, it will remain at 0 forever, right? So what are we looking at? We are trying to see if this particular 0 solution is Lyapunov stable, perhaps asymptotically stable, perhaps exponentially stable, right? So if I want to see Lyapunov stability, then what is the definition? Basically, for a given epsilon, does there exist a delta such that if x0 absolute value is less than delta, then that implies the absolute value, I mean here they are scalars, so norm and absolute value is the same, is less than epsilon for all t greater than or equal to 0. And in this particular case, I'm going to basically say, given some, this is a choice, right? For a given epsilon, it could be any number. Can we find a delta? It could be as simple, as small as possible. The bigger, the better, actually, because the easier to find such a delta. Because if you want to remain in a big region, you can pick a very small delta and remain in the region epsilon. But as you start decreasing the epsilon, then it becomes more and more difficult to find that delta, and then that is pretty much about this start close, remain close concept of Lyapunov stability. So the problem always exists when epsilon is very small. So however small I pick this epsilon, can I find a delta is the question. So I'm going to basically say let this delta be exactly equal to epsilon, okay? And then for all x0 less than epsilon, we know the solution is e raised to minus t x0, and of course e raised to minus t x0 absolute value is indeed less than epsilon for all t greater than or equal to 0. So this is certainly the 0 solution is being lazy, and then use this short form Lyapunov stable, right? The next question is this asymptotically stable? Well, it so happens that this e power minus t x0 goes to 0 as t tends to infinity, irrespective of x0. So that means this is globally asymptotically stable, right? Remember, local stabilities are basically, can you find a region around which this system behaves well? In the sense of Lyapunov stability, we have this very weird definition of epsilon delta. When it comes to asymptotic stability, it's fairly straightforward. Is there a region around the equilibrium point? If you perturb within that region, will you go back? In this particular case, the solution is such that we will essentially go back to 0 no matter where we start, right? Whether we start in the negative side, positive side, anywhere we converge to 0, because negative exponential is going to go to 0. And then the final obvious thing is actually this is also globally so 0 is Lyapunov stable, right? 0 is convergent, right? So we have global convergence and Lyapunov stability. So that gives us globally asymptotic stable notion of the equilibrium point. And of course, this is also globally exponentially stable. How do I know that? Well, I mean, if you remember, basically we need to show that this is some kind of positive alpha e raised to minus beta times norm of x0, right? So here x of t is e raised to minus t x0. So essentially alpha could be greater than 1 and beta is exactly equal to 1. That's it. And then we satisfy that. So we get globally exponentially stable, right? So, but please notice that in this particular example, we had to find a solution, right? And we had to do this math to figure out, that is indeed true, right? So if we didn't have a solution, the alternatives are, suppose somehow we know that there are solutions to this particular, some particular differential equation, then we end up essentially, doing this math for a limited number of initial conditions. Why? Because you know if we know that there is a numerical solution, then we can use numerical methods to solve. So we can simulate it and then see if some of these things are satisfied for that particular initial condition. But how many initial conditions are we going to check? So if we don't have a closed form expression, then it becomes almost impossible to apply this definition and check, verify it. There is no verifiable test using numerical simulations, right? So, and it becomes almost impossible to check for any of these notions. So anyway, let me just, for the heck of it, I will go through another example. Again, it's a scalar example, just to show that we can do this, right? So this, we can do this d by x cube, right, is equal to dt, and multiplying 2 on both sides, I'm going to get d of x minus 2 is equal to 2 dt. And if I integrate it, I'm going to get something like this. Okay. So simplifying it, x square of t is essentially 1 over 2t plus, let me put some c where c happens to be equal to inverse of this x square of 0, right? So therefore x of t is square root of 2t plus c. Okay, where c is dependent on x square of 0. So the question is basically, can we show anything about stability? To start with, at least fortunately, right? I mean, the question becomes whether it's plus or minus. For the time being, let's pretend that we don't know how to find that answer. Perhaps both of these things will satisfy this x rod equals minus x cube, and that leads to the question of multiple solutions and so on. But for the time being, let's ignore. But either way, even if it is plus or minus, you can clearly see that there is an asymptotic convergence, because as t gets bigger and bigger, this denominator gets bigger and bigger, and then therefore we'll have a 0. Is this exponentially stable? I will leave it up to you to think, and then most probably it's not. And because 1 over square root of t may not behave like a exponentially decaying function, right? So I'll leave that question to the audience, right? So what about finally the question of Lyapunov stability? Can we find this given an epsilon, right? Can we find delta such that for all x delta, then x of t is less than epsilon? Well, I mean, basically substitute that xt there, and when we do this math, we'll get something like this. And when we rearrange this, we'll get 1 over epsilon square is less than 2t plus c, and then we should have c less than 2t minus 1 over epsilon square, and c happens to be 1 over x 0 square, and we can try to find this, right? Now you can clearly see that at 0 this is less than 0. It does not make any sense. So you have to be careful, and perhaps delta cannot be found just that easily. So but you see that I'm not even trying to find whether this particular system can be shown to be Lyapunov solution through using the solution, because you've seen that even though you know the solution, finding these epsilons and deltas the way we defined actually happens to be a very difficult task, even for a simple example like this. And if you have more complicated examples, then basically things get more complicated. Even finding a solution, once we find solution, this finding epsilons and deltas is even more difficult. So this epsilon delta is there for us for our understanding, but in reality we need to find a better approach to actually show some equilibrium point is Lyapunov stable or asymptotically stable, right? So let's go back to our slides, and then basically we just saw a couple of examples where we showed that it is almost impossible to do it if it's slightly complicated expression, except some simple thing like a linear system. So we will have some method that Lyapunov gave, who gave the definition, and also a method to verify these stability notions, and we define something called Lyapunov function candidate. It's a straightforward simple thing when we see it, and then the main theorem, the Lyapunov stability theorem, using these Lyapunov function candidates and Lyapunov functions, and then we can actually eventually show asymptotic and exponential stability. So for all these things we'll have some interesting conditions, right? So the next set of slides are basically a bunch of results, these things, and then we go back and forth in trying to prove these results, and we won't get into too many technical details, but actually it's nice to understand the idea of the proof, perhaps geometrically, if not anything else, right? So eventually we need to also get some results on global convergence and global stability and things like that. So let's start off, right? So in our view, basically we are trying to understand the stability of equilibrium of this particular ODE, x dot equals f of x. So this particular equation is going to haunt us for a long time, so we'll keep using that as the main system, right? So we call a function, right, mapping in this particular case some subset of D, which may or may not contain the equilibrium point, but typically it has to contain the equilibrium point. Then we assume that the equilibrium point is at 0, is positive definite. With this function v is positive definite if v of 0 is 0 and v of x is positive for all non-zero, right? Not non-negative but positive. And it's essentially what we are trying to say is 0 is a local minimum for this particular function, right? In the case of global result, you can imagine this may have to be global minimum, right? And probably much more. So if it satisfies this positive definite condition, which is fairly straightforward to understand, we call that as a Lyapunov function candidate. It's one of those terminology thing, and there's not much we can do about it. There's a typo there. So again, let me repeat. V is a Lyapunov function candidate if it simply satisfies this positive definite condition, which says that v of 0 is 0 and v of x is positive, right? And we define, and then this is grand abuse of notation. We do that throughout this particular course. We call this v dot of x. It's actually a function of x. V dot is like a symbol there rather than indicating its with time derivative in this particular case, right? And basically that's the shortcut for calling something like v prime of x, which is, you know, a row vector comes from taking the derivative of x, right, times f of x. So it's the inner product of you know, the gradient as well as the dynamic function f of x, right? So it's simply a function of x, something that we are interested, but this function is not something arbitrary. If I actually substitute, instead of x, if I substitute the flow s of t comma x0, which is a time dependent function in that particular case, this v dot indeed becomes the time derivative of this v of s of t comma x0. So in that sense, this v dot of s comma t s of t comma x0 is not an abuse of notation. It's actually the real derivative, time derivative. But v dot x, you know, when we don't see any explicit dependence on time, that's kind of an abuse, just a short form to denote v prime of x, f of x, right? So where are we going with all these things? I'm going to just jump ahead and say, if a Lyapunov function candidate, that means it's a positive definite function, satisfies one more condition, this v dot is strictly less than 0 or less than equal to 0, then we call it as a Lyapunov function, right? You know, one is a candidate, the other one is a full-fledged function. And then obviously we're going to say something if we have a Lyapunov function, right? So again, you know, consider this ODEx dot equals f of x, where f of 0 is 0. That means the 0 is an equilibrium point. And let v be a function that is Lyapunov function candidate, and we know what that means. V of 0 is 0, and then v of x is positive for all non-zero x, right? Then we assume this v dot of x, which is v prime of x times f of x, is less than equal to 0, right? Just that. So if these two conditions are satisfied, then we call this as a Lyapunov function. Anyway, then we conclude, and it's a beautiful conclusion, that the zero solution is Lyapunov stable, right? So I want us to understand the terminology. Lyapunov function candidate means simply there is some positive definite function, and if it satisfies the second condition, that is v dot less than equal to 0, v dot of x is less than equal to 0, which is a function of x given by v prime of x times f of x, the inner product between those two vectors, is less than equal to 0, then we call that function actually as a Lyapunov function. So essentially what we are saying is, if for a given ODE, if we have a Lyapunov function, then the zero solution is Lyapunov stable. Okay. So before we go on to the next results, let's try to understand proof of this, right? Go through a very rigorous proof. You know, the algebraically it's quite verbose and quite technical at times, right? But we get a fairly good idea in terms of how this can be shown. So what do we need to show? Given an epsilon, you know, some number, we want to show that there exists a delta such that if we start within that delta, then x of t will remain in epsilon, right? So what are we, I mean, and we are saying that we can find such epsilon and delta if two things are true. V of 0 is 0 and v of x is positive definite for all non-zero. That's one condition. And this v prime of x v prime of x times f of x is less than 0 for all non-zero x. I mean, this of course is 0 at 0 anyway, right? Yeah. So how do we connect it? I mean, that's the brilliance of Lyapunov result, Lyapunov function result. So the technicalities are basically, you know, what region around the origin can we take and things like that. But eventually we can actually figure out how to figure out those smaller regions and things like that. So we have a zero equilibrium point, right? And we construct now this epsilon. Epsilon is something that we choose, right? So I have this epsilon ball, okay, and that's my notation, right? And I want to find out a smaller delta, a ball, and if I start within that delta, then I will remain within this ball, right? So how do we ensure that can happen? Okay, so I'm going to do the following, right? So let's see. So I'm going to basically take this boundary of b sub epsilon, right? Let's sorry. The typical notation is basically this del boundary, which is just the circle there. Okay. On this boundary, I am going to minimize the function v of x. Okay. And I don't know, I'm going to get some alpha or something like that. Okay. So what do I know about this boundary? You know, the maximum value, minimum value of this v of x is alpha. Okay, so then I'm going to do this strange thing. Define a level set of all x's such that v of x is less than alpha. Okay, so of course this I'm going to write it separately. You know, if you take this set d alpha, this may look something like this. Perhaps there is something like this, right? I mean, in the 2D space, you know, it could be 3 islands that satisfy this particular condition. But one of the islands will have to be, will have to have the origin, right? Why is that? Because v of 0 is 0, so therefore, you know, even if you have 10,000 islands, one of the islands will have to have 0 in this, because you can clearly see v of 0 is 0, and which is certainly less than alpha. So this d alpha will contain one of the islands as actually um, basically the origin, right? So take that island. So the technical jargon is basically take the connected component of d alpha, you know, that contains the origin. So let's call that something like this. It may or may not touch, you know. So I mean, even if it touches, it barely touches because it's an open set, whereas the boundary is containing. So it's possible that the actual set may look barely touching this, and then something that looks like this, right? Let me erase the other one, right? Or it's possible that it's entirely within. Okay, but what's nice about this d alpha is, right, if I start within d alpha, okay, so v of x is less than alpha, right? So some number between 0 and alpha. But what do we know? We know that v of x of t is decreasing. How do I know that? Well, because we know that v dot of x of t as a time derivative, which is as a function of x, is nothing but v prime of x of t times f of x of t is less than 0. We know that. So v dot as a time derivative is less than or equal to 0. So the v of x of t is going to be decreasing, right? So therefore, you know, even if it starts, perhaps it may go around and things like that, but it will never go to the boundary, especially beyond that, because on the boundary of this particular epsilon ball, every v value is more than alpha, you know, not just equal to alpha, but more than alpha, right? Some of the technicalities is basically, does there exist such a alpha and things like that, and then a lot of these nice fundamental real analysis results that guarantee us existence of such an alpha and things like that. You know, just to those who are curious, basically a continuous function defined on a compact set will always have a minimum and a maximum and things like that. So all those nice deep results come into picture when we actually try to guarantee that this happens, right? So again, the argument goes that if you start within, it will never reach the boundary. So it will have to be within this this thing, right? So so therefore you pick some ball that is completely uh, within this d sub b island, the island that has the origin, right? So it could be that. If you want to be optimal, you know, just basically pick a circle that barely touches this particular thing. You don't have to be optimal at all. So now what does it say? Even if I start here somewhere in the delta, I'm going to never go out. I'll always remain within this, and therefore I will remain within this ball. So I found my, for a given epsilon, I found my delta, right? And I didn't use the fact that epsilon is small or big or anything like that, as long as these conditions are satisfied in that region, right? So there's that technicality. You have to figure out this epsilon ball, you know, within the delta ball small enough that basically where all these nice things are satisfied. So there is no reason that this alpha is, I mean the d alpha, you could pick not for alpha but maybe much smaller, okay? So that so you can pick much smaller delta region than trying to be optimal and things like that, okay?